Yeah, Assalamualaikum and good afternoon. So we'll continue with the lecture for angular momentum addition. So let me just recall last time was to look at this spin and orbital angular momentum addition. So we have gone through it, and somewhere towards the end, I sort of stopped. Let me just go down there because I was thinking of something which looks a bit strange. The fact that this course was rarely being taught, so I didn't quite put much thoughts on some of the formulas. But when I did, yes, no, on Monday, and then it's sort of okay. This looks puzzling. So the idea is one is getting all this. Initially was this. So what we wanted to do was to look at how the states in the couple representation is related to the case with the what you call uncoupled representation. So we have found out by using step-down ladder operators that this is one of the coefficients that we have actually obtained. And then the other three that we need is obtained through identifying the fact that the Clebsch-Gordan coefficient has to be matrix elements of a unitary matrix. And the unitary matrix, by convention that we have adopted, is going to be real. So in other words, a real unitary matrix is a orthogonal matrix. So we come to the point of writing down your 2 by 2 orthogonal matrix, okay, which looks like this, and we identify the first entry over here with the first entry here, okay. Then we obtain all the rest, and we obtain the necessary relationship between the couple representation eigenstate, which is essentially the eigenstate of your total angular momentum, which includes your orbital in this case with spin angular momentum. And your spin angular momentum has spin up and spin down, so you have another one over here which has L minus a half instead. And essentially these are the what you call expression in terms of the uncoupled representation. So here you see your state with ML here, and then state with MS here, spin up, okay, and then this ML again, and then spin down, okay. So in other words, these are just linear combination of this upper component and lower component of your spinner in some sense. So now that brings us to this particular point. We actually get a position representation of this. So you sort of multiply your unit vector basis, and this is going to be dependent on your theta and phi coordinates. And then basically you should be getting your angular momentum states as spinor functions, okay. And this is where I got a little bit puzzled because I've never taught this deeply before. You find your angular momentum, well, okay, in the first place, if you remember your Lm, your orbital angular momentum, if you take essentially your position representation, this is just your spherical harmonics spherical harmonics function, okay, which depends on theta and phi. And in those cases that we have discussed before in the first course, your L and M is restricted to integers. Okay, so over here is just your standard spherical harmonics. Okay, but what you find over here is the fact that you're going to get this addition of a spin half. Okay, here is minus half, here is plus a half. And how do you actually define this was not really thought seriously before, but that's where I have to mention what it is, so that we don't just use this label and then sweep everything under the carpet, okay, without understanding what that what this symbol means. Okay, so this has to come. Remember that, okay, the spin part of the Hilbert space are given by this chi plus and chi minus, usually written in terms of these states. Okay, so you get this representation in this spinor wave functions, but you need to define what this is. Now, if one simply just simply write down what your spherical harmonics is. So let me just write it down without telling you what it is. So your spherical harmonics is a product of two functions. One is your associated Legendre polynomial. So that will, in this case, I'm just simply writing down the labels here without really understanding it. So this will be cos theta, and then your function that depends on phi will be just your exponential here. So here we'll just straightforwardly equals to exponential m minus a half times phi. And similarly down here, yes, let me write everything down in full. So this will be PL m plus a half cos theta. Cos theta is the argument of the Legendre, associated Legendre polynomial. And then this is exponential I m plus a half phi. Just right there. Okay. So there is no problem with this function of phi, but there is a problem with this function because it has not been defined before. Now, when I look up the literature, actually this is not really quite well known. Okay. The normal thing that we had, as I mentioned earlier, your PLM. Okay, maybe I should go to the web page. Your PLM, so this is spherical harmonics Wikipedia. So let's look downstairs if it's actually been defined. So in other words, here is defined as your associated Legendre function here, Legendre polynomials, you can see over here, but this is limited to the case of m to be integer. So what is this Legendre function when m is not, when the label here is not integer? So apparently this is not really being known to many. So when I look up the literature, there is one paper that essentially discuss what it is. This is actually a 1999 article. There are some articles before that, but this is probably the best article that I can find, and there's already a table of the Legendre function written down in this particular paper. So what is the problem with the original Legendre function is the fact that your original Legendre function is defined on a sphere. Okay, so on a sphere, when it depends on theta and phi, when you rotate 2 pi around the phi direction, for example, then one should get back to the same physical point. But you already know that something is actually not quite the same when you involve spin. So there must be another way of getting this, so which is not defined on the sphere, but will be defined on some maybe a kind of a cover of a sphere. Okay, so I will not go into the details because it's quite complicated. Well, I mean, not that much complicated, but you have to go into the main theory. So it has been calculated out. Essentially, when they solve for it, there are more labels for us to look at. So here is your M. Okay, your L is restricted to well, in this case, the integer case, but your M will now be able to what you call take up half integer values. But in addition, there are other labels which sort of classify the functions differently, and but essentially you can what you can do is now you can actually find all this PLM with half integer what you call quantum numbers. Okay, so in other words, it can be defined, but it needs resolving the eigenequation, and then in that particular case you'll get some extra things. Okay, so this is actually in this paper which is written by Hunter and et al. Okay, and I will try to upload this paper onto the Twitter blast for you to have a look at. Okay, but the point I wanted to say is, going back to the notes, is that we know now what this is supposed to be. There is such a function that defines this associated Legendre function with which has half integer values. Okay, so it's not something just swept in under the carpet under the labels and you don't know what it is. Okay, you have to recalculate what this is supposed to be. Okay, so that more or less what I wanted to say for that part, which I stopped thinking about it in the previous lecture. So the next thing that we want to say, just to end this part of the lecture, is to see that these functions are essentially it's a simultaneous eigenfunction of L squared. This is the couple representation. Okay, it's a eigenfunction of L squared, eigenfunction of S squared, eigenfunction of J squared, and then of course Jz, the Z component of the total angular momentum. But then what happens is that you also know that your J squared can be written as, so this is really J dot J. So maybe I should write that down, J dot J. And remember, there are tensor products inside here, so I'm not writing out the tensor product now. So this is really equals to L plus S dotted with L plus S. And of course, you're going to get your L squared plus your S squared, and then you're going to get your 2L dot S. But remember that this whole thing is your J squared, and J squared commutes with all the other operators over here. Okay, so in other words, L squared is also commutes with all these operators, S squared also commutes with all these operators. So in other words, L dot S is also an operator which is coming from your J squared, should also be what you call compatible with all these observables. So in other words, the eigenfunctions that you have is also an eigenfunction of L dot S. Okay, so which is convenient, and then you can find out what this L dot S eigenvalues are by just substituting your expression here. So you get JJ plus 1 here, LL plus 1 here, and then this is half plus 1, and essentially you get two different kind of values depending whether it's L plus a half or L minus a half. Okay, so that more or less tells us, okay, later on when we talk about excuse me, later on when we talk about spin orbit coupling, you know that, okay, you have all this L dot S interaction terms that would somehow tell you, when you do all the calculations that involves the total angular momentum. Okay, so I hope that clears up the matter why I sort of stop at that particular point last lecture. Okay, so you can try to Google. It's not that easy to get, but no, you can get a few papers, but I think the paper that I showed you just now, this one is probably the latest that I can see, and I will try to give it to you later on. Okay. So the last part of this lecture should be talking about rotation matrices, and then how Clebsch-Gordan coefficients or Clebsch-Gordan expansion can actually tell you a little bit more about the rotation matrices. Okay, so if you remember a rotation operator previously, you would have some rotation axis. So generally you can have this axis that projects onto a particular direction, so that will be your rotation axis, and then this operator can be given some kind of matrix form by expanding it with respect to the total angular momentum eigenstates. So this is essentially what we have defined before as the Wigner functions for rotation. Okay, and then usually what happens is we fix up this particular J. Okay, and then essentially because of why is this so is because if we look at what's involved, let's consider this equation, for example. This is J squared. Okay, your J squared is a commuting operator. Okay, and then if we look what's inside the rotation operator over here, okay, it's J dot n, but J dot n and J squared will commute. Okay, because these are just your Jx, Jy, Jz. Okay, so J squared and J dot n will commute, and that also means that J squared and your exponential also commutes. So in other words, I can swap these two around, and I get dr J squared Jm and dr J squared Jm. You know how this operate on the eigenstate, so you get Jj plus 1 h bar squared. So in other words, dr Jm is an eigenstate of the angular momentum J squared with this eigenvalue. So when you take say something like this, J dash M dash, then you know that this will be 0 if your J and J dash is not the same. Okay. Oops. Right. So that tells us different matrix element with different J will not be will be 0, and essentially what can happen in this particular case, you will get a block of a block representation of your rotation operator. Now, you might ask, if one concentrates on a specific J, why do you want to bother about this? It's the fact that later on, okay, so in other words, what happens in general, a rotation operator might be becomes complicated in a way that you have several other blocks coming into the picture. Okay, so this happens, for example, when you take composite rotation operator, one acting on a particular basis J1 M1, okay, and the other one is acting on another set of bases J2 M2. Okay, so this J1 M1 will be forming a sub-Hilbert space, and J2 M2 will be forming another sub-Hilbert space. The whole space will be spanned by the tensor product of 2, but this is in the uncoupled representation. Okay, so you can go to the coupled representation and then you find out, okay, the product of these two rotation operators will somehow be under suitable basis change. It will be somehow transformed into this block diagonal kind of rotation matrix, rotation operator, sorry. Okay, so you can see that, okay, the addition of the angular momentum goes from modulus of J1 minus J2 up to the point where it gets to the maximum, which is J1 plus J2. Okay. So generally, a product of two rotation operators, okay, in this case, can be expanded in terms of the coupled representation in this following way, and this is said to be forming what we call a Clebsch-Gordan series. Okay, and how is this so? Is the fact that, okay, let us write down the matrix elements of this tensor product thing. So there will be the first one will be acting on J1 M1. Second one will be acting on J2 M2, so there will be a matrix element M1 M1 dash, and then M2 M2 dash as an example. And then if one were to expand this with respect to let me see, expand this with respect to figure out what's going on here. J1 M1 M2 M1 dash M2 dash. Okay, so what is happening over here is probably I'm missing something. Let me just recall what I did earlier. See if there's any. No, not this. There must be a different equation that I'm following here. Yeah, okay. So this will be the left-hand side. So yes. So remember that this thing should be related to the total rotation operator. Okay. So if you take the total rotation operator, okay, for the left-hand side, take the matrix element, and then you essentially get that. Okay, and that reduces to this. Okay, and this is defined CJ1, J2. This is already being defined in terms of your rotation, the total rotation operator here. Getting confused now. I think at some point there must be okay. Let me. If we look at this, these are essentially just plugging in your identity operator. J1 dash. Sorry, I'm getting really confused about this. So remember, there are two that in this rotation operator. There's a tensor product, okay, because it acts on two different Hilbert spaces. So here I'm just decomposing your rotation operator into two parts. Okay, one is acting on your. Remember that this. Let me just write it down so that you can see what I'm saying. So this one is really what? This one is simply J1 M1 tensor product J2 M2. So I'm just decomposing this into a tensor product kind of thing. So this will be just the matrix element in one Hilbert space, and then this will be another matrix element in another Hilbert space. So basically you get that two matrix elements. And then what's going to happen is I'm going to plug in an identity operators. Let me just see where to put it in. So I'll be putting it one over here. And then the other one is over here. So I'm just putting identity operator here, identity operator here. Okay. So what happens in that particular case, you can resolve this identity operator. But now what we really want to do is to resolve it using the couple representation. So basically you have the couple representation for the identity operator here, your projection operator here. Okay. And then the other one would be this one. This one. Okay. The two bra and cat at the very end is just the same thing. Okay. So these are again your identity operator resolved according to your total angular momenta J dash M dash, and this one according to J and M. So that means you need to sum over J and M here and sum over J dash M dash. Okay. So what happens there is that here you get your Clebsch-Gordan coefficient. Okay. And then essentially this will be the matrix element with respect to J and M. Okay, and J dash M dash. But J and J dash has to be the same, otherwise it's going to be 0. So you get your delta J and J dash there. So now this will be the matrix element. Okay. And then this will be again another Clebsch-Gordan coefficient. Okay. And this will again, as you see from the Kronecker delta, it will now broken up into the different J's which is given in this particular Clebsch-Gordan series. Okay. So let's consider this particular case of J1 equals to L1, J2 equals to L2. So your rotation operators according to some orbital angular momentum, and then you let your M1 and M2, M1 dash and M2 dash to be 0, and then you actually take, for this, you actually take, remember that this is the matrix element, okay? Now you actually take your, so what I'll do now is I'm going to put this one now resolve according to position representation. So when you resolve to position representation, then you'll be getting your spherical harmonics. So what you have here is essentially a multiplication of spherical harmonics. Instead of the matrix element, you have spherical harmonics multiplied together, and then this will be related to the right hand side given into this particular form. Okay. So finally, with this, essentially this is like an identity for your spherical harmonics. Okay. So what one does in this particular case is to multiply with, since we have one spherical harmonics over here, so one multiplies with another spherical harmonics, in this case by L and M, to the whole equation. So that means I'm going to multiply this by YLM, but what I really want is YLM star, so that it becomes something like LM ER kind of thing. So this gives you YLM star. Okay, so I get multiplication of that, and then that should be integrated over theta and phi to get rid of your theta dependence and your phi dependence. So you integrate over your, this is solid angle. So this is just your d cos theta d phi. Okay, and what you're supposed to have, essentially you'll get a quantity which is independent of theta and phi, and in fact this is actually given by over here, if you integrate, so you integrate YL M, Y, and this is star, and this is YL dash M dash over the solid angle, that should give you delta L, L dash, delta M, M dash. Okay, so that get rid of that spherical harmonics, and then essentially what you have is this integral over three factors of spherical harmonics. Two of them is from the uncoupled representation, and one of them is from the coupled representation, and these are given in terms of these factors, and this factor is essentially a Clebsch-Gordan coefficient, but now you can see that the fact that you have actually get rid of your M to be equals to M equals 0. I think above I mentioned that. Okay, and then oops, why is it not moving down? And then so that is a Clebsch-Gordan coefficient that is independent of M1 and M2, and then you have another Clebsch-Gordan coefficient over here, and this will be an identity that is being used in problems of spectroscopy, for example. And the fact that this is independent of your L and M, sorry, this part, okay, is a consequence of a theorem that we shall discuss in the next lecture, okay, the Wigner-Eckert theorem. So there are a lot of this, a bit complicated kind of angular momentum kind of analysis, because when you do a composite system, you're going to encounter this addition of angular momentum. Okay. At this juncture, is there anything that you want to ask? Let me go here. Or should I just continue? Yeah. How is that integration done? Okay. Let me go back to the notes. You mean this one? Well, all of these are going to be functions of theta and phi. Okay. So in other words, your d omega is what? D omega is d omega is that. So and then your d phi will now let me just write in terms of the two integral. So phi from 0 to 2 pi, and then d cos theta will go from -1 to +1. Okay, so when you integrate with respect to theta and phi here, all the theta and phi inside this integral should be how should I say, should be averaged out in some sense, okay, to get some quantity that doesn't depend on theta and phi. I'm not sure if that answers your question or not. No, you have to remember, even in ordinary spherical harmonics, let me see if it's on the website or not. You have to go back to perhaps the first course of quantum mechanics. Let me see, yeah, this kind of thing. Okay, but now instead of the two, this is just a normalization. Sorry, this is just a normalization condition. Okay, but well, this one. Okay, and this one is the orthogonality thing. Okay, so the one that we had just now is actually an integral over three spherical harmonics. One of the spherical harmonics actually belongs to the coupled representation, and the other two is actually belongs to the uncoupled representation. Does that answer your question? It's a bit tedious in some sense. There are you have to remember that any states in this particular case would be angular momentum states can be given the form of a wave function by going to the position representation. So now everything is done in terms of wave function. Your spherical harmonics is just wave functions, and then when you integrate them, you're supposed to it's just like integrating over or summing over your eigenstates, okay, and that should cancel out somehow. So I hope that is just an example of what things are done in terms of angular momentum kind of calculations. I can tell you the kinds of things that people do with angular momentum calculations in the old days. they've written tables of it. Let me show you example, a whole book. I don't want to go through this book, of course, but there's a whole book on just theory of angular momentum. Okay, let me go to page 1. Maybe I'll go down to the table of contents. So some of these things, once you know how to do it, by right, you should be able to do it in principle. But of course, that doesn't mean it's easy. But the idea is to introduce you how can you do all these calculations. Okay, so here you can see there are a lot of different things over here. You have the Wigner functions again, and then you can get pretty scary at times. So I don't want to go through this. I just want to give you, okay, what are the tools that you need to do all these calculations. Okay, so that is a book that actually I bought this book. Cost me a fortune. But never mind. Right, so now perhaps, what's the time now? 3:42, still a long way. So let me go to the next lecture. You probably have gone through mathematical physics at some point, right? So in mathematical physics, one talks about vectors and components, and then how these components may change under change of basis, and then you generalize your vectors to tensors, right? And then these tensors will also have components which also change under change of basis. Now, the one that you're probably exposed to in mathematical physics are just vectors and tensors in the classical sense. Our problem with quantum theory is that all this idea of vectors and tensors are done in terms of an operator form. So one needs to be able to understand how the behavior of these operators and the change of basis, and how does it connect with our previous understanding of vector components and tensor components. So this is essentially this lecture is about that, and then finally at the end we will talk about Wigner-Eckhart theorem, which is the thing that I mentioned just a few minutes ago. Right. So let us recall how you change basis in ordinary classical mechanics is to do rotation kind of transformation. So that why is rotation okay? You probably have seen it before. It's because it keeps the magnitude of the vector to be invariant. So you have to remember there's some property of the vector, so to speak, has to stay invariant. Okay, so in this particular case, normally you will think of your length of the vector will stay invariant under a change of basis. Okay, so your length squared, for example, of your vector is unchanged. So how you actually change basis, and you start to rotate the basis, and so on and so forth. Okay, so how would that actually translate to quantum theory? Is that this part of rotation matrix should now be translated into your rotation operator that we have been studying all along. Okay, But now, okay, what's the analog of this thing? Okay, this would depend on the set of operators. Now, here you have to think of here, for example, I have Vx, Vy, Vz. So in other words, I should be considering a set of operators that correspond to this kind of components. Okay. So how is this going to be done? Is to consider the kind of an expectation value of the set of components here. So here's a set of operators correspondingly to the components of the vector Vx, Vy, Vz. Okay, and you can actually rotate this expectation value, okay, to give a new expectation value given by the rotation operators here. So this sort of does the rotation, and that will correspond to the other side of this well, mapping. Okay, so your expectation value should behave the same way as you expect for the classical case. If you rotate the basis, then your expectation value will also be rotated in that sense. Okay, but this is with respect to an operator that should have a specific behavior under rotation. Okay, so what is that behavior? Is the fact that this set of operators with the components here v1, v2, v3 will transform under this unitary operator to give you a rotation matrix times this operator. Okay, so that is the sort of the quantum classical corresponding, because what we did is essentially this thing. Okay, so this has to be equals to sorry, it's already there. This has to be equals to that. Okay, and if you just remove your psi over here, you get the behavior of the vector operator that you need. Okay, so any vector operator should behave accordingly. We shall see in a few minutes what is some example. So one of the things that we can actually try to do is perhaps consider an infinitesimal rotation with respect to some direction. Here is with respect to n direction. So one can actually write down this d dagger as 1 plus I epsilon j dot n on h bar, and then you have this operator vi, and then dr again, you just use this one. Okay, and that should be equals to rij vj. And if you expand this out, okay, you should be getting vi plus epsilon over I h bar of the commutator between vi and j dot n. Okay, so this is a general equation for infinitesimal rotation. So you can see now that your algebra is coming in. Okay, so this you'll see later on correspond to your rotation algebra, Lie algebra. Okay, so let's be more specific now. Let's consider the z-axis. So the z-axis, then your rotation matrix will look like this. Your z component will not change. Okay, but your the other components of x and y will change. Remember, this is supposed to be cos theta minus sine theta, cos theta thing. Okay, so your cos theta for theta infinitesimal will just give you to first order equals to 1, and then this will be minus epsilon, and this will be epsilon, and this will be 1. Okay, so this is a infinitesimal rotation matrix about the z-axis. So that goes there. Okay, so now what happens when you do that? Oops, let me just. Now this one will be now jz, because these are rotation about z-axis. So I will have now this combination. So let's suppose I take I equals to x, or the first component. Okay, so I get Vx plus epsilon on I-ish bar Vx jz equals to, and then you multiply the rotation matrix with Vj here, and then you get Vx minus epsilon Vy, and you can see that this will cancel off later on. And then the same thing happens for I equals to y here, and then finally I equals to z. And if you look at the final thing, you can actually rewrite the whole thing as follows, which is something that you have seen before. Okay, remember ji jj equals to I-ish bar sum epsilon ijk gk. Okay, so that tells us, okay, what is this? This is just your rotation algebra, but now applied to the a much more general set of operators. This one is really saying what? This one is saying that your J is really a vector operator. Okay? And if you have done well enough of the first course, you should be also getting this. This is saying that, okay, your position operator is also a vector operator. And also your momentum operator in 3D is also a vector operator. Okay, so you can see that, okay, I can have more structures with respect to the operators by seeing this analogy between the classical case and the quantum case. Okay, so I think I'd better stop there, because going into tensors will probably take longer time. So are there any question at this stage? Let me take the attendance here. No. As I said much earlier in the course, much of this second course tells you how to deal with more realistic systems so that you are able to do calculations. The one that you did in the first course are mainly just the fundamentals, and not enough to do practical calculations. So that's probably the end of my lecture today. Any questions before we go? I know it's a bit difficult at this stage, and I don't have a proper set of notes for this advanced course, because I keep, I only taught this course I think about 4 times, and each time I teach, sometimes I change things, so I don't have proper notes for this. So I'm doing it Well, I mean, the first few has no, the notes are already there, but no, the next few lectures, I'm going to be a bit more scattered in some sense because I don't have notes. So any kind of questions at this stage, if you want to ask? Guess no. So okay, I know it's quite a lot to take in. Some of the things that's been discussed is also no are not familiar to many people. So, but if you look at all the advanced books on quantum mechanics, the later chapters of say some quantum mechanics book, they will have all these elements coming in. Things like perturbation theory, which will hopefully we'll go through it. So I'll stop there for today. Thank you, everyone. Right. Bye.